In this video, we're going to work through the optimization problems from the Miss Brown worksheet, 3, 4, 5, 6, and number 9. So number 3, an open rectangular box with a square base is to be made from 48 cubic square feet of material. What dimensions will result in a box with the largest possible volume? So let's see if we can draw what this is going to look like here. So we're going to have something that looks like a box, and it has no top, and the base is a square. So since the base is a square, we know that these two sides are the same length, but that might be something different. Now, if we know that the area is 48, we also know that the area is going to be there's 5 rectangles that make up that area since there is no top. So there's going to be the bottom, which is x squared, and then each of the 4 sides is going to be x by h. So the area is going to be x squared plus 4xh. We're going to need this so that we can get h in terms of x. Now the volume, the thing we're trying to maximize, is going to be length times width times height, but since our base is a square, ours is going to be x squared times h. So this is what we're trying to maximize. The problem right now is it's got 2 variables in it. It's got both the x and the h from the x squared h. So we're going to come back over to this relationship here and see if we can solve for h in terms of x. So if we subtract the x squared to the other side, and then we can divide by 4x, we're going to get h is equal to that 48 minus x squared all over 4x. And I think we might be better served if we split that up and simplify. So we can think of that as 48 over 4x, and then a minus x squared over 4x. So with a little simplification, I think we can get the 48 divided by 4 is 12. And I'm going to write that as x to the negative 1 for derivative purposes here shortly. And then I'm going to write the x squared over 4 as a 1/4 x. I think that's a little easier to see in terms of derivatives as well. So our volume is now going to look like x squared times, and the h we're going to replace by that 12x to the negative 1 minus 1/4 x. So let's go ahead and distribute that. So that'll become a 12x to the first, I guess, and then a minus 1/4 x cubed. This is what we're trying to maximize. And I don't think we can restrict our domain any. It sounds like to me that just domain is going to have to be, x is going to have to be positive. We can't get a 0 or negative side length in a box. So our derivative of the volume is going to be 12 minus, and that'll be 3/4 x to the second. We want to set that equal to 0 so we can look for critical points. So I'm going to add the 3/4 to the other side. So that's going to make that look like 12 equals 3/4 x squared. We can multiply by 4/3 on both sides to get the x squared by itself. And that works out really nice because we get x squared is 16. So x could be either a positive or negative 4, but in our case only the 4 is going to be in our domain. Only 4 is a reasonable choice for a side length. This is good news. We can, because we only have one critical point, and we're going to try to argue that this is an absolute maximum. So if we look at our derivative, and we're going to plug in a number, say in between 0 and 4, maybe 1 would work. then we'll get the derivative is going to be 12 minus 3/4, so that's going to be positive. If we put in something bigger than 4, say maybe 8, because that'll cancel nicely with the 3/4, 8 squared is 64. 1/4 of 64 is 16, times 3 is 48. 12 minus 48 is clearly negative. So this is good because now we can make the claim that the volume, see, what are we trying to find? The dimensions that will result in a box with largest volume. So I'm going to say the volume will have a relative max at x equals 4 because v prime changes from positive to negative, period. The volume will be an absolute max because x equals 4 is the only critical point. I'm running out of room here. So there's our argument, making our case for why that's the absolute maximum. We need to give the dimensions, and our dimensions are going to be x by h. And let's see, h is back over, where's the easiest place maybe to put it in? Should we try there? So if x is 4, then our h is going to be 12 divided by 4 minus 1/4 times 4. 12 divided by 4 is 3. 1/4 of 4 is 1, so that'll be 2. So our dimensions for our box that has maximum volume is going to be 4 by 4 by 2. Okay? Let me see if I can slide this up a little bit. And I'll make it as big as I can so I have a little more space to work in. So a container in the shape of a right circular cylinder with no top has surface area 3 pi. What height h and base r will maximize the volume? So this is similar to what we just did, where we know what the area is and we're going to try to maximize the volume. So we have a cylinder here that has no top. So the volume of a cylinder is pi r squared h, and the area of that rolled up part is going to be 2 pi r h, and that's the rolled up part, and then we'll have only one circle since it has no top. So that's going to be pi r squared, and we know the area is 3 pi. So again, we're trying to, like we saw in the previous problem, we're trying to maximize the volume, but the problem there is our volume has an R and an H both in it, and we need to get it to where it just depends on one thing. So we're going to come to our area formula and try to solve this for R. So we're going to get 2 pi r h. We'll subtract that pi r squared to the other side. Then we're going to get the h is equal to, and we're going to divide that by 2 pi r. So let's see, we have 3 pi over, that'll be 2 pi r, and then we'll have a minus pi r squared over 2 pi r. Let's simplify that a little bit. We can cancel the pi's, and I'm going to call that 3 halves r to the negative 1, and then minus, see, we can cancel the pi's and one of the r's, so I think that's going to be 1/2 r. So this is our h. So now our volume formula is going to be pi r squared times that 3 halves r to the negative 1 minus 1/2 r. Let's go ahead and distribute that. So we'll call that, let's see, the 3 pi over 2. We'll kind of lump all the constant together. And the r squared times r to the negative 1 will leave us with only one r. And then we're going to have a minus, and I'll call that pi over 2 when the pi multiplies the 1/2. And the r squared times r is going to make that r cubed. So that is the volume that we are trying to maximize. So we are going to go v prime, and we're differentiating with respect to r. So that's going to give us 3 pi over 2 minus, that's going to be 3 pi over 2r squared. So there's our derivative. We're going to set it equal to 0 and look for critical points. So I'm going to add the 3 pi over 2r squared to the other side. So we've got 3 pi over 2r squared equals 3 pi over 2. That's kind of nice because 1 is going to be r squared. R can be a positive or negative 1. I guess we should say our domain is going to be that r must be greater than 0. So that means our only critical point is going to be r equal to 1. So very similar to what we did in the last problem. We're going to look at our domain, or we're going to look at a sign analysis of our derivative of the volume. So there's our 1. And our derivative was over, let's consider it maybe over here. So if we plug in something like, say, 1/2, 1/2 squared is 1/4. So that's going to make this part smaller than the 3 pi over 2 there. So I think that's going to make that be positive. And if we plug in something like, say, 2 for r, then the 2 squared is 4. That will make the negative part bigger, so that's going to make our volume be negative. So our claim that this is an absolute max is going to be very similar. We're going to say V has a relative max at r equals 1 because V prime changes from positive to negative, period. Now that's just a relative max. V has an absolute max at r equals 1 because r equals 1 is the only critical point. So we've made our case that that's an absolute maximum. So it was asking us for the height and the radius. So if r is equal to 1, that's going to be our radius. And our height, remember, was all of this kind of craziness over here. So if we plug in 1 for the r, we're going to get 1 to any power is 1, so it would be 3/2 minus 1/2 is going to be 2/2. So the height also is going to be 1. So the dimensions of our cylinder of largest volume with a surface area of 3 pi has a radius of 1 and a height of 1. Kind of the closest thing you can get to like a cube if you were thinking of this as like a prism. Okay, number 5. A sheet of cardboard 3 feet by 4 feet will be made into a box by cutting equal size squares from each corner and folding up the edges. What will the dimensions of the box with largest volume? So we're starting with this cardboard, and it's going to be 3 by 4. We're going to cut squares out of the corners, and we'll say those are going to be x by x. And when we fold that up, we're going to get a box that looks something like this, and it does not have a top. So there is no lid to that thing. So it's looking something like that. Now the volume of a rectangular prism is length times width times height. Now this original dimension that was 4, remember we're cutting 2 of those x's out and then folding it up. So that's going to make this side down here 4 minus 2x. This side that was 3 to start with, we're cutting out 2 of those x's. So what's left is 3 minus 2x. And what's getting folded up is going to be the height. That's going to be x. So our volume is going to be 4 minus 2x times 3 minus 2x times x. Well, we're going to try to take the derivative. Let's see if we can multiply that out a little bit. I think the 4 times 3 is 12 times x is going to be 12x. We're going to get a 4 times negative 2 is negative 8x. Negative 2 times 3 is a negative 6x. The negative 8x and the negative 6x makes negative 14x times that third x is going to be a minus 14x squared. The negative 2x times the negative 2x is positive 4x squared times that last x will make it 4x cubed. So our derivative is going to be 12 minus 28x plus 12x squared. Now we're going to look for critical points here, but let's pause a moment and see if we can't restrict our domain and narrow our search here a little bit. Now I'm going to come over here. I'm going to look for some room. I'm going to come up and carve out some room here. So we know that one of those dimensions is 4 minus 2x. So that length has to be positive, the width has to be positive, and the height has to be positive. So from the 4 minus 2x greater than 0, we can say negative 2x is greater than negative 4. Then if we divide by the negative, it changes the direction of the inequality, and we get x less than 2. Similarly here, we're going to get x is going to be less than 3/2, and then we have x is greater than 0. So we want the more restrictive of these because we want both of these to be true at the same time. So our domain is going to be, let me write that a little more clearly. Let's say our domain is going to be that x has to be bigger than 0, but less than 3/2. Okay, back to our derivative of our volume. Let's see, I think we can factor out a 4 here. So if we factor out a 4, that's going to be 3x squared minus 7x plus 3 that we're trying to make equal to 0. Now, as often happens on these problems, this is not going to factor. So we're going to need to get what x is either by using the quadratic formula or kind of our new strategy, since we're going to have to use our calculator anyway, is to graph that and find the 0. Now here's where the fact that we've restricted our domain is going to make our life a little bit easier. So if you just graph with an x-min of 0 and an x-max of 3/2, and then you calculate the 0 by going second trace and option number 2, finding the 0, you're going to get to 3 decimal places that x is 0.566. Now, you don't want to use that rounded answer. Now you can also see, let me hold off on that a moment. So when you're graphing that derivative, you're also going to help us make that case for the fact that this is an absolute max. So the 0.566 is our only critical point on that domain, and you can see that it's going to be positive to the left when you graph that derivative and negative to the right. And so we can make that similar argument that v has a relative max, hopefully this is getting more comfortable, at x equals 0.566 because v prime changes from positive to negative, period. V has an absolute max at x equals 0.566 because x equals 0.566 is the only critical point. Okay, now we were asked to find the dimensions. So our dimensions, remember, are the length, width, and height. And those are going to be x, 3 minus 2x, and 4 minus 2x. So our dimensions are, we have the height is 0.566. Now to get the width, we should store that exact value point of that came from the graphing menu before we do any computations with it. So I still have mine up on my calculator, and it's right off the graph. So before I do anything else, I'm going to go second mode. That's going to take us to the home screen. Then go store, which is right above the on button. X, that X comma T comma theta button, enter, and that will take all the decimal places of accuracy and put it in as X. Then we can go 3 minus 2x, and we'll get our width is going to be 1.869, 1.869, and our length is going to be 4 minus 2x. So similarly, we'll go 4 minus 2 and hit that X button again, and that's going to be 2.869. 2.869. So those are our dimensions for that open top box that has the largest volume. Okay, I'm going to slide this up a little bit. And now there's a different kind of question. We want to find the point on the graph of y equals square root of x that is closest to the point 4, 0. So let's see what we're looking at here. Here's going to be our graph. We know a square root of x graph looks like this, and I'm going to call this point 4, 0. Now, we're talking about any point on here. So one of these, as we look at different points on there, you can see there are going to be different distances to that point. So this generic point we're going to call here is going to have x for its x-coordinate. And because it's on the curve, y equals square root of x, its y-coordinate must be square root of x. Now we need the distance formula. The distance between 2 points is Pythagorean, so it's given by the square root of x2 minus x1 squared plus y2 minus y1 squared, and then we square root that whole thing. So our points, our x2, y2 is going to be the x comma square root of x, and our x1 comma y1 is going to be the point 4, 0. So we're going to say distance is going to be, we'll go x minus 4 squared plus, and then it'll be the square root of x minus 0 squared, and we'll square root that whole thing. So we're going to multiply that out. So that's going to be first one squared, twice the product. Oops, twice would be 8. So that's going to be an 8x plus the second one squared. And the square root of x minus 0 is square root of x. Squared is going to be x. And that's still, for now, in the radical. So we'll clean that up a little bit and call that x squared minus 7x plus 16. That's all in the square root. Now, this is what we're trying to minimize, so we want to find the absolute minimum of this distance formula. So here's where we can get away with something. I'm going to say that I'm going to have to state this, the value of x that minimizes d equals the square root of x to the second plus, was that a minus? That was a minus 7x plus 16 is the same x that minimizes, and I'm going to call it d hat, that doesn't have that radical, the x squared minus 7x plus 16. That is, whatever makes this parabola, the smallest, it's not going to somehow change the ordering when we put it in the square root. So since we'll get the same value of x, we can do our calculus on this function instead of this one, which is going to have a much more complicated derivative. But I have to tell people that's what I'm doing. So now I'm going to take the derivative of d hat, and that's 2x minus 7. I'm going to set that equal to 0, and so we'll get 2x equals 7, so x equals 7 halves. Ooh, we better think about the domain here. Well, let's see. Not sure we can really say much except that for our domain, because it has to be defined in that square root function, our domain is going to be just x greater than or equal to 0. But that's okay because we've only got one critical point, so that's our good news. So if we look at our d hat prime, and we're going from 0 to forever, we'll put 7 halves right there. So if we plug in something between 0 and 7 halves like 1, we can see that that's going to make our derivative negative. If we plug in something bigger than 3.5 like 4, then we'll get a positive. So this is good news. So like we've seen before, we're going to say d hat has a relative minimum at x equals 7 halves because d hat prime changes from negative to positive, period. D hat has an absolute maximum at x equals 7 halves because, I'll just say 7 halves is the only critical point. Okay, so we've argued that it's a maximum. They said find the point. So our point, remember, was going to be x comma square root of x. So our point is going to be, the x value is 7 halves, and the y value will be the square root of 7 halves. And we're free to just leave it like that, and we no longer have to rationalize. Kind of nice. Okay, let's then move on to number 9. So I'm going to slide this up and see this one. I'll try to make it as big as I can. Let's read it and then I'll enlarge it so I have more space to work on. Find the dimensions of the rectangle of largest area which can be inscribed in the closed region bounded by the x-axis, y-axis, and the graph of y equals 8 minus x cubed. So 8 minus x cubed. Let me try to blow this up a little bit. So we know that y equals x cubed looks like that, and the negative will reflect it in the x-axis, and then the 8 is going to move it up 8. So what we're going to get is something that's going to be coming down here and then continue on. This is the part that we're interested in because we want the region bounded by the x-axis, the y-axis, and this curve. Then we're going to imagine now inscribing a rectangle inside this region right there. Now let's see what else we know. We know that this is going to be 0, 8 up here at this point, and the question is, where does it cross the x-axis? Well, let's see. Let's set it equal to 0. So that means that 8 is going to equal x cubed. So that means that must be at 2. So this point right here is 2, 0. So this is nice because since our rectangle has to be inscribed in there, we can restrict our domain and say that our domain is going to be 0 less than x less than 2. And you could make an argument, I think, and say that it could be equal to 0 and equal to 2, but you'd have to be able to live with a rectangle that has area 0. And it would make our calculus easier, but it might be a little harder to defend in terms of an actual rectangle. Now, we know that the area of a rectangle is base times height. Let's see, now the base of our rectangle is going to be this distance right here. This point right here is the key to this because it's a point that is shared by our geometric figure, but it's also a point that's on our curve. So its x-coordinate is x, and because it's on that curve, its y-coordinate is going to have to satisfy 8 minus x cubed. So back to our rectangle, this base of our rectangle is exactly the x-coordinate of that point, and the height of our rectangle is exactly the y-coordinate of our point, which means our area is going to be a base of x and a height of 8 minus x cubed. And so if we distribute that, that means our area formula is 8 minus x to the fourth. This is what we're trying to maximize. So the way we do a maximum is we take the derivative. It's going to be 8 minus 4x to the third. And we're going to set that equal to 0 to get our critical points. So that's going to make 8 equal to 4x to the third. If we divide by 4, that's going to make x to the third equal to 2. And so we get a good news, bad news situation. The bad news is cube root of 2 isn't all that great to work with. The good news is that's the only critical point on our domain, and it is in between 0 and 2. So this is the good news part. So we're going to say there's 0, there's 2. Here is the derivative of our area. Our only critical point is that cube root of 2. Now, cube root of 2 is bigger than cube root of 1, and the cube root of 1 is 1. So if we plug 1 into our derivative, plugging in 1, 8 minus 4 will be a positive, and plugging in something bigger, like say, let's see, well, maybe 1.5. I'm trying to think what we could do that would make this easy to see. I think we can see that at cube root of 2, that's where 8 minus this is going to be 0. 8 minus 4x cubed will be 0. So as we move to the right of the cube root of 2, this 4x cubed will be bigger than 8, so their difference will become a negative. And now we're back to familiar territory. We're going to make the argument that this is the absolute maximum. So A has a relative max at x equals the cube root of 2 because A prime changes from positive to negative, period. A has an absolute max at x equals the cube root of 2 because x equals cube root of 2 is the only critical point. Okay, so we made the case that it's the maximum. We're supposed to find the dimensions of that rectangle, and our dimensions are the base and the height. So the base was that cube root of 2, that was just the x, and the height was going to be that 8 minus x cubed, so that's going to be 8 minus the cube root of 2 cubed, so that's 8 minus 2, which is 6. So our height is going to be 6, and our base is going to be the cube root of 2, and those are the dimensions of the rectangle with largest area. All right, very good.